In this video, we'll cover an introduction to dienes. So di meaning two and ene meaning double bond. So a diene's got to have two double bonds. The most simple diene is 1,3-butadiene. And this bond can be rotated about, but it does take a little bit of energy because you break the pi system up, the overlap between those two central carbons. So 1, 2, 3, 4 carbons in a row. All of these carbon atoms have p orbitals on them. And those p orbitals are all in line when that's planar. So we can have pi electron density sort of spread out through the entire system above and below the plane of the molecule. So to rotate about that is going to temporarily break this. So this is going to be planar in nature. We call this the S-cis conformation because you are able to rotate about that single bond. And that's in equilibrium with the S-trans, which is the major conformer. So trans, because they're opposite one another, the S stands for sigma, meaning single bond, because that's a single bond. It's just a sigma bond, and the S-cis and the S-trans just refer to the relationship of those terminal carbons to one another. So we're going to do a couple of classifications. We can have a diene that is acyclic, meaning there's no cyclic system in there. You can also have dienes that are cyclic and part of a ring system. And then we also have where those double bonds are in relation to one another. So we could have two dienes, a diene where the two double bonds are right next door to one another, so they're in a row there, and that's called conjugated. And this is going to be the most stable type of diene because that pi system is all connected and those p orbitals can line up together. So that portion of the molecule here where we have these pi bonds is going to be planar because all those p orbitals will line up next to one another. Next instability is what we would call isolated dienes. And so this has two double bonds, but in between those double bonds I have sp3 hybridized carbons there. So this would be called an isolated double bond, and it is less stable than a conjugated double bond because the p orbitals are separated by sp3 hybridized carbons. And so then the lowest in energy is something called cumulated, which you really won't see much of. Cumulated double bonds are when they are next door to one another, so I'm going to put a circle for that other double bond. These are the type of compounds that you see generated under very kind of harsh conditions, so where there's not much thermal energy. You'll sometimes see cumulated systems in interstellar space where it's very, very cold and there are no neighboring molecules generally. And so things that we would deem to be very reactive at room temperature can exist in those cold, harsh conditions for a very long time. But it's not very stable, and at room temperature you're probably not going to see one. If we think about what's going on here, if we draw those three carbon atoms in a row, I've got one pi bond on this side, and then I have another pi bond, but it can't be overlapping on the central carbon the same way that the first one is. It's actually going to be orthogonal. So I'm going to draw the new p orbitals, or the additional p orbitals, like this. And so those are overlapping in front and in back. So blue is in front and in back, and red is above and below. So the hybridization of that central atom is actually sp hybridized. So these terminal guys will be sp2, but the central carbon only has two groups coming off of it, the carbon atom on either side. And those p orbitals are orthogonal to one another, so there's no stabilization provided there. And that's the reason that we don't see cumulated species generated very often. So let's take a look at the preparation of dienes. And there's sort of the industrial way to do it, and then there's also, so this is an R, sorry about that, the industrial way to do it, and there's also what we would do in the lab. And you're already familiar with the lab ways. What we do in industry is called thermal dehydrogenation. So what we do is we take some alkane that we generally isolate from fossil fuels. So when we go drill for oil, things like that, it comes up as a mixture of a lot of different alkanes. We separate them out from one another, generally via distillation, so that we can use them for different applications. Depending on the length of the carbon chain, it'll have different properties and therefore could be used for different applications. What we do then is we can take some of those alkanes and we can just heat them really, really hot in a reactor, and then we use some kind of metal catalyst, and that gives us alkenes on the other side, plus H2 gas, which has the benefit of being explosive. And so this process has to be pretty carefully monitored, and the H2 gas has to be collected and monitored in the plant. If we're in the lab, which some of you might decide to do this semester, we know two ways to do this. We know dehydration reactions, and so in a dehydration, of course, I would lose an equivalent of water. So say I already had one double bond, and then I have OH here. I just need to put something in solution to make OH a decent leaving group. And then when we look at this, we've got alpha, we've got beta, beta prime, and beta double prime. So you would think that there would be three possible alkenes that you see, but the only one that will be made is the conjugated system. So unless it's not possible to make a conjugated diene, that's all you're going to see. What you usually see here is some sort of H+. It can actually be a pretty weak acid because this is going to make a pretty stable product. What we see as our product is only the conjugated diene. So it would be, I'm going to draw this H over here, the removal of this H and this OH to give us a double bond, and we're familiar with the dehydration reaction mechanism, which proceeds to be either E1 or E2, depending on the substitution of the alcohol. So then the other method that we are familiar with, I'm going to use kind of an analogous system, is a dehydro halogenation. So this will be done under basic conditions, and again I'm only going to see the conjugated system because that's the most stable product by a long shot, as we just discussed earlier what the relative stability of dienes is. So this is a dehydro halogenation, so minus HX. Bromine is already a good leaving group, and so we just need a base to come pluck off that proton. This will proceed through an E2 mechanism because of that strong base. It's very good at plucking off the proton, so it will pluck the proton off of the beta carbon, fold those electrons in, and kick the leaving group off in a concerted step. So the only time that you won't see a conjugated system made is when the starting material makes it so that it's not possible. So if we look at this guy here, I'm going to change pen colors. I've got an alpha carbon, and then I have beta here, and this would also be beta because they're two methyl groups, and here I have no H's. So if there's no H's at that position, then I cannot pull off another proton, so it's not possible to make that product. So what you would see in this case is an isolated diene, and that's because conjugated is not possible. In this case, because you don't have any alpha protons, or any beta protons, excuse me, at that next door neighbor position to make the conjugated diene.